Great, we have reached the last section of this chapter, 2.6, ROS parameter server. Did you know that nodes will always use parameters to accomplish their goal? ROS allows us to set parameter values from a number of locations, including the command line, launch files, and RQT reconfigure. This is possible thanks to something called the ROS parameter server. This parameter server uses a shared multivariate dictionary. If you're not familiar with multivariate dictionaries, you can refer to a Python tutorial. Dictionaries are types where variables of different types can be saved together in a long list of, and can be a long list of values. And this parameter server is available through network APIs, meaning that we can access the parameter server through C++, Python, and other languages. These nodes are used to store or retrieve parameters right before we execute our nodes. They're not for high performance usage because we cannot change or use these parameters at runtime. They're used statically right before a task or an experiment is executed. Nodes, unlike nodes, parameters are not published. The parameter values are always available to all nodes through the parameter server. Some examples that might motivate the use of a parameter server might be cases where, for example, you want to load controller gains and manipulating an arm. Those gains would be valuable to you at the beginning of the experiment because those gains have been hand-tuned. Or imagine you're using cameras that need calibration. You have two kinds, intrinsic or extrinsic, and so you need to load all of those parameters at the beginning of the task in order to fine-tune your camera vision. Sometimes you have robot models where you might switch a hand of a robot which might have different properties, say the length or a radius, and so those are parameters that you might also want to load according to what model of the robot you're loading. The ROS parameter server allows us to easily save parameters to something called the YAML files. The YAML files use markup language to encode the syntax, and they're very easy to use. Also, these YAML files can be easily loaded through launch files or even the command line. When are the values loaded to the node? Well, these values are loaded statically at the beginning before running our nodes. The values of these parameters cannot be changed during runtime, so they're not dynamic. In case you want to do dynamic modification of parameters, you can use the RQT reconfigure system. Just as we have tools for nodes and messages and services and topics, we have a command line tool for parameters called ROS param. This tool allows us to set parameter values to the server by providing a name and a value. We can also get them or retrieve them if they already exist on the server. We can load files or dump parameter names and values to files. We can delete them or list them. We'll look at the use of ROS param in just a second. Let's turn our attention to the example parameter server package. And within the launch folder of this package, we have two files, the launch file and the YAML file. The YAML file will have PID gains for a controller that we want to load through this launch file. So let's go ahead and open that launch file using ROSet. Let's try that again. Actually, let's do ROScd. And we go into the launch folder. And here we can look at that join1 gains YAML file. We see that this parameter, join1 gains, will have, or we see that this file will have three variables, P, I, and D, with the equivalent values. In the parameter server, join1 gains will serve as a namespace. So all of these three values will be preceded by this namespace before listing the values. We'll see how that works in just a second. This is also using a Python dictionary notation where we have the keys, PID, and the values. The syntax is important, and if you're not familiar with it, please refer to a Python tutorial. Okay. If we want to access these parameters from C++ or Python, then RosCpp and RosPy provide APIs for us to do so. In RosCpp, parameters can be read or set using two different methods. The first one depends on the node handle. Here, for example, after creating a node handle nh, we can call method getParam. This getParam method requires the global name of the parameter in the parameter server, and then that value can be automatically stored in a local variable, here global name. This can later be used for whatever purposes you have in your code. The second alternative is using the node namespace. Here we use a more general method called RosParamGet, pass in a relative name as opposed to a global name, and then save this to the local parameter. RosPy is more flexible and gives us a choice of doing all of this using the same getParam method, but just providing a different name. For more details, please look at the links at the top of this slide. Okay, so what we want to do now is use a C++ example to read parameters from the node. We're going to look at read param from node.cpp. So let's go ahead and open this file. And here you'll notice that right here in main, we initialize, we have a node handle, and then we have, we're creating three local variables for the PID gains. Then we use our node handle with the getParam method and that global name joint1gains_p to save the value. We print it out to screen using rosinfo, and if this is not found, which sometimes can happen if the value hasn't been properly loaded to the parameter server, we can issue a warning. The task is repeated 2 more times for the D gain and the I gain. So once you compile these examples and have properly set your system, then you can load the gains through the launch file and then read them through this node. Let's try. So the first thing we want to do is load them. As we run the launch file, we get information from the parameter server that these 3 parameters have been loaded onto the system. And by the way, we can use the RosParam command line tool to further examine any of these parameters. For example, we can say RosParam list to also see these numbers. We can say RosParam get to get their values. So, for example, DPI in this case. We can use RosParam set to change them. Let's change I from 8, say, to 10, and then retrieve that new value. And in the same way, we could use it to delete it. Okay, now we can also run the node to read those values directly. I just modified this, rosrun example parameter server, read parameter from node. And you'll see that immediately we can rosinfo print to screen the values for PID. Although here we made a mistake and set proportional gain 3 times. Very well. this wraps up section 2.6 and our chapter as well. And I hope you found this chapter significantly educational, very useful to learn a lot of things. We learned a lot about ROS messages and how critical they are to define custom topics for publishing and subscribing nodes, but even more so, they play a critical role for services and actions determining the kind of requests and response that they're going to have. We looked at services as a client-server paradigm. We looked at how they are blocking systems. They can be one-to-many. They have synchronous communication with a quick reply. And we looked at ROS actions that are used for long-term duration tasks, how we can have access to different callbacks from the client and manage that information, especially the feedback. We looked at how we can cancel requests through the API. And also we looked at the ROS parameter server and how it is shared by all nodes and how data can be loaded or read from the command line, but also from launch files and C++ code. The homework for this week, will train you to learn some Python programming. We'll do that first by using basic publishing and subscriber nodes, building on concepts from last week, and then we'll move to ROS services where you will do the tutorial in Python for a ROS service, the basic tutorial. And finally, the more challenging part of the homework is looking at a ROS action found in Baxter code called the Joint Trajectory Action Client. And here you can learn how this action might be implemented in a real robot to move a robot arm. So I hope that is interesting to you. Thank you for joining us this week, and I look forward to seeing you next time, where we will be learning more about simulation. See you next time.